So the final lecture, yeah, it's going to be Chern Moser theorem. And you remember I wrote a theorem by Cartan yesterday, which is, it was done for a connected open set containing 0. And it says that if you have a self-map sending 0 to 0 and the derivative at 0 is the identity, the only choice for the biholomorphism is to be the identity. So now we are concerned not with open set, but with the boundary. And we ask, is there some kind of same result, finite jet determination? Okay, so let's start. In the previous lecture, what did I do? I was considering M W is Z bar. Just, we are doing that in C2. It's already enough. So my variable are Z, W in C2. This is called the tangential variable and the transversal variable. And if you put an A here, there is no problem. This is Levi non-degenerate. It's really important to have this ZZ bar term. And we computed what's called this infinitesimal CR automorphism. You remember, it's a real vector field that are real-analytic. Okay? So this is M and Aut, and we computed completely this guy, and we saw that this is 8, and what we saw is that the coefficient of this Z, remember, it's given by the Z holomorphic vector field of the form C, A, G, Z, D, D, Z, J, such that real part of Z restricted to M and Aut is equal to 0. This is exactly that. And we saw that, in fact, the coefficients are always polynomial of degree at most 2. You remember that? You have the decomposition. Holm M and Aut 0 is given by first component of degree -1 plus G minus 1 over 2 plus G naught plus G1 over 2. And the final, the bigger one, is G1. And it's given by 1 over 2 W squared dW plus ZW something. Okay? So this is the biggest polynomial you can have. Now, we are now interested in the general case. It was what's called the model case. Now your M, for the time, the rest of the lecture, will be given by MW is, it starts the same as M and Aut, but you have higher order term. Just smooth is enough. You don't read, yeah? I don't understand. This is Holm. The definition of Holm for me is the set holomorphic Z. You don't like the capital letter Z because they are variable. I agree. This is not the same Z. I should. Like that? Sorry, yeah. But I have a W also. But you agree. This is small z, and this is capital Z. Okay? Okay, now I'm interested in real Levi non-degenerate hypersurface. That means what? That means it's given by a function phi of z, z bar, real W, which starts with a non-vanishing term here. You can normalize it to be 1. Usually it's not the case. It could start with z square, z bar, anything. But I really want to have Levi non-degenerate hypersurface. You will see why in a moment. Okay, and the question is is there an analogous of Cartan theorem? So the question is, the problem is, classify or characterize all the biholomorphism map from M to N, the self-map. Biholomorphism means that they extend in an open set of M as a biholomorphic map, holomorphic, and the inverse is also biholomorphism. And you know, we just have that because it's a sense in the germs of M. So since M is defined near 0, you better have h of 0 is equal to 0. Okay. What can we say? Is there a number of finite jet, number of derivative enough to completely characterize the biholomorphism? That's a question. And for that, remember, we always we put the weight 1/2 to z and the weight 1 to w, even though now you have higher order term. This is just this part which enters in the choice of that. Sure, you have z cube, z blue, a lot of different terms. Just you have also d phi of 0 is equal to 0 and phi of 0 is 0. It's always the same stuff. So it's a little confusing. I will say biholomorphism, but in the literature you see automorphism. And then it's difficult. Is it infinitesimal automorphism or is it automorphism? So I prefer to talk about biholomorphism map. By the way, it's also called, H is in what is said the stability group of M, fixing the origin, stability group. This is a set of all germs of biholomorphism, group of M. Okay, so now it's time to state the theorem. Maybe not quite, just what is, no, I can do directly the statement of this theorem. This is back to 74. So the theorem is due to Chern and Moser. And I think it goes back to 1974. Okay? And it's not only in C2, it's for a real hypersurface in Cn plus 1. But I am just doing in C2. So let M be a real hypersurface. M sitting in Cn. Capital N will be always Cn plus 1 because we have just one equation. Then its biholomorphic map sending M into M are determined uniquely by two jets at 0, by there. It's better English, I guess, because it's wrong. By there, two jets at 0. What does it mean, two jets? Two jets means that it's a h of 0, the first derivative at 0, and the whole. So in C2, what does it mean? In C2, you need to know h of 0, which is 0, so there is nothing to do. You need dh over dz at 0. You need dh over dw at 0, d square h over dz square at 0. What else? Yeah, now you understand. And d square h over d. Okay? here there is no weight involved. When I say it's a real derivative, not weighted derivative. The two jets, it's all the derivative up to the second order, okay? As long as you know them, then there is nothing to do. There is just one. This is the theorem of Chern and Moser. So we are going to prove it. And remember, this is for any m with phi, just you assume that this guy is not 0, okay? That there is ZZ bar. If there is no ZZ bar, there are counterexamples, right?
The theorem is in C2?
I'm Cn plus 1, but I'm stating, yeah, it's in Cn plus 1. It's for hypersurface because it doesn't work anymore if you go to higher codimension. And, but for, you know, it's easier to prove with just one variable, okay? Unless you really want that I prove with a lot of variable. I'm not willing. I think you have a lot of indices, so. And the key point is what we did yesterday. That means we only care about this part and the Holm M0 at 0. So what is the proof? Proof. Proof. So you have your H. You have your H sending M to M. H of 0 is equal to 0. And in fact, let's assume it's not hard to see that you can always do that, that H1, there is two components. H is H1, H2. So you can assume that H1 ZW, it's Z plus F of ZV, ZW, where F of FZW, their weight, big, look, this is of weight, 1/2, and then I can assume that all the weight in F are bigger than 1/2, okay? Weight in F are strictly bigger than 1/2. And H2 starts with W plus G of ZW, where G, this is the weight is 1. In fact, there is no Z because of the form. You know, it sends M to M. And if you look at the form, you can easily see that phi of Z bar. If you take this form, as I told you, for phi, phi of 0 is equal to 0. And d phi of 0 is equal to 0, it implies very quickly that there is no Z involved. And G, weight in G, are bigger than 1. And there is no Z square either, because Z square cannot, but it's not very hard to see that. And now what do? You use the equation. There will be a basic equation because M goes to M. So what does it mean that M goes to M? So just to reflect the weight, F of ZW, I will decompose into weighted component, okay? With respect to Z has weight 1, 1/2, and W weight 1. So I'm going to write like summation of F mu ZW for the weight, for the chosen weight. And we know that mu is bigger than 1/2. And the same for J. G of ZW, I'm going to write like summation with respect to the weight. You know, I decompose with respect to a polynomial of weighted weight mu. G nu of ZW with nu bigger than 1. Mu bigger than 1. Mu bigger than 1. Okay. So you have that. So I decompose this part, and I let this ZW, in front. So now, what does it mean that H send? Remember, H has to send M to M. That means that W plus, this is the equation, I replace W by this one. And I replace ZZ bar by H1. And I evaluate at W in M, right? So what do I have? I get to I get W plus G ZW minus W bar plus G bar Z bar W bar over to I equal phi of what? H1 is Z plus F ZW. Z bar is F bar plus F bar Z bar W bar. And real W is W plus G ZW plus W bar plus G bar over 2. This is the equation I get, right? And I restrict to M. It's valid only on M, right? So what do I get? W is what? W is S plus, where is my, here. The imaginary part in W is given by that. This is the imaginary part. So it's given by S plus I phi ZZ bar S, okay, plus G of Z S plus I phi ZZ bar S minus S minus I phi ZZ bar S plus G bar Z bar S minus I phi ZZ bar S. Okay? And the same here. You replace S plus I phi ZZ bar S everywhere. But look at this first term. What happened? The S, you don't get, and you divide by 1 over time, right? So what do you get at the left? You are left with which kind of equation? The S disappears. And you are left with phi. You see, you have I phi minus minus plus I phi to I phi over 2I, it's phi. So you get phi of Z bar S plus, I'm not going to write all the time, it's just the imaginary part of G at Z evaluated at this guy, okay? It's exactly what you get here. And I will leave the right-hand side, so it's phi of Z plus F evaluated at M, Z bar plus F bar evaluated at M, and it's going to be what? It's going to be S, real part, I mean. It's going to be S plus real part of G evaluated at M. So you have that. And here, it starts with what? If I evaluate it, I should say, it's going to be S plus real part. It's going to be S plus real part of G. And here, I will do a Taylor expansion at Z bar S. So what is the first term I get? It's phi of Z bar S plus term which involve F and G. So the good news is that they cancel out. And you are left with an equation im G of Z bar S plus I phi Z bar S, which will start, you can even compute because you will have Z F bar plus F bar Z bar. You see, maybe I can just give you the first. It's going to be Z plus F times Z bar plus F bar because you assume that you have a Levi non-degenerate plus, you know, a lot of terms which appear higher order. Okay? And now, what you want, I want to extract the smallest mu0, the smallest weight here and here. What I do, I should, this is without weight. Now I have that, I have this equation, I have not talked about weight. Now, I want to see the smallest mu0, the smallest weight. What kind of equation, if you compute it, it's going to be, you see, it's going to be Z times F bar at what? Z, but you don't take the whole phi, because you want to have, it's going to be what, the smallest one? S plus I Z bar. Because if you take the other one, it's going to be bigger. It's something like that, plus Z bar F computed at, so it's going to be Z S minus, I guess, minus I S plus, no, what do I do? Anyway, I'm going to, the first term I Z F bar plus F Z bar plus higher order term. So you have that. And you want to extract the minimal order from this equation. So, as an exercise, which is not hard, you can show that the minimal mu0 you get satisfies the following equation. So extracting the minimal term, the minimal weight term in mu0, you get what? I give you the answer. You have to get, but I think you have already an idea because this is 2 real F Z bar, okay? But you remember F is given an S plus I phi. So you have to forget about the perturbation, which is important. It's the S plus I Z bar. So you will get exactly 2 real part of Z bar, the term mu0, which is the first one in my decomposition of F mu0 minus 1 over 2. This is the first at Z. And here you take S plus I Z bar. You forget about the rest of the term. And this is what you get here, the minimal term. And here, the minimal term you get is im J0, J mu0, evaluated at Z, S plus I Z bar. Because if you plug in the different order term, you are not in weight mu0, you will have bigger weight. So it's really what you get. And now you can understand why you choose 1 over 2 and 1, because this is of weight 1, this is of weight 1, and the rest doesn't count. And look at this equation. What is the importance of this equation? This weight, you don't see the perturbation of M, you just see the model. It doesn't depend of the rest. You know, remember, M is given by im W is phi of the bar real W, which is z bar plus high order term. But you don't see them. You just see the model hypersurface. And now, I don't know if you have an idea of what it is that. How can you relate to the stuff I did yesterday? You know, f mu 0, it's a polynomial. It's a weighted polynomial. It's a holomorphic weighted polynomial. Also, okay? So what is your guess? How is it related to what I did yesterday? What's that? This is a holomorphic stuff. This is holomorphic. So I'm considering this guy. You know, the first term of f, ddz plus g mu 0 ddw. This is a perfect holomorphic vector field. What is the guess? This guy is in Holm M0. That's a fantastic, but maybe let's check, we have time. So what does it mean to have, remember, M0, it's given just by the truncating. You just forget about all the stuff you don't like. So let's apply Y to this guy. So what is that first? So what do you get? F mu 0 minus 1 over 2 at M, at Z, S plus I, Z bar. Now, differentiating, you get what? Minus Z bar, okay? Plus G mu 0 Z S plus I Z bar, because I'm living on M, and ddw, it's just 1 over 2I, right? And now I bar, to be in Holm, I need to add the bar. So what is the bar? It's F mu 0 at Z, S plus I Z bar, right? Times Z plus G mu 0 bar at Z, S plus I Z bar, 1 over minus 2I. And if you are not too tired, you can see that it's exactly the expression I have here. If I put that at the other side, I get 0. It's exactly saying that this guy is 0. It's exactly the same. So this is equal to 0 using this information. It's writing this, it's exactly putting that here, multiplied by 2 or divided by 2, so it's equal to 0. So you see the relationship. You have a biholomorphic map, and it's enough to study its model. For sure, I did that in the Levi non-degenerate case. But there is no reason that you could not try to use this method with different weight. So what does it mean, really, that this guy has to be in Holm M0? That means that F mu naught cannot be of degree. What are the possibilities for M mu naught minus 2 and G mu naught? We saw that you can only have mu naught is of weight linear or degree 2. Okay? That's the information. So the corollary of that, now, it's not finished. Say you have two maps. say you have a map H, which is an M to M, and H1 and H, oh no, it should not be H because I have already, and K, another map that have the same two jets. They are biholomorphic map. That means, so assume that they have the same, assume that these two maps have same two jets at 0, right? So you write H as Z plus what we did, blah, 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 and K, you decompose your map, I think. I mean, H1 is Z plus F1. H2 is W plus G1, okay? And you have K1 is Z plus F2, and K2 is W plus G2. So you do that. How do you show that if they have the same jet, two jets, they are the same? What do? You just you compose H with K minus 1, for instance, okay? It's still a map which goes from M to M. And what is this map? They start H, K minus what? It's the identity plus what? Plus jets of order, since they have the same two jets. They cancel. And you get something with either order at least 3, okay? But this is not possible, since there is nothing. The first term cannot be, there is nothing, because the first, the minimum mu0 has to be of order 1 or 2. So there is nothing here. There is nothing here. That means what? That H is equal to K. Because if you extract the mu0, the first term, polynomial term, has to be here. But since they have the two jets determination, it cannot be possible because it's at least of order 3. And there is nothing. There is nothing on it. So it's a contradiction. So nothing happened here, and then H is equal to K. So you see, you need biholomorphism for that. And in fact, M, you can do this for smooth CK. You don't need all the smoothness of your M. So you see, you understand how it goes. This is a very, very, very nice argument that goes back to, I don't know, Tanaka also has this kind of argument. I think it's Moser here. And it was used because a lot of papers have, with a more general hypothesis, it was possible to solve this finite jet determination. So, I have a few things more to say. How many minutes? Yeah. So maybe I should now say which paper, if you want to read more about this stuff. There is a paper, where is it? It's a paper of Moser and Chern. The paper I'm talking about, it's the second part of that. Moser. No, Chern and J. Moser. And the name of the paper is Real Hypersurface. Real hypersurfaces in complex manifold. In complex manifold. and it's in Acta Mathematica. I can give you the exact reference, 74, and even. So it's the first, you see. And I can now give you some information that it's a research going, it's not done. I mean, there'll be a lot of improvement to the Levi degenerate case. The Levi non-degenerate case is completely understood, and there is a lot of question about Levi degenerate case. I will just mention a paper done with Zaitsev and Kolar, Martin Kolar. Maybe I just give you the reference because we use this kind of method, similar method. Oh, no, so I should not raise here. The reference, it's, I think I have here, I should give you the exact reference. Do I have here? Yeah. This is really on the line. It's Chern and Moser operators and polynomial model. In CR geometry. And it's Martin Kolar and and Dmitry Zaitsev. It appears in Advances, Math, in 14. So you can guess polynomial model. Here we just talk about what kind of model? Of degree 2, because it's ZZ bar. But you can replace the Levi non-degenerate by a polynomial of degree D and ask for some regularity. You know, we have Levi non-degenerate, and it's going to be replaced by more general condition, which is in fact holomorphically non-degeneracy, if you know this condition. Okay, here we have Levi non-degeneracy. We did, but I cheated a little bit. You know the proof is more involved, but the idea is here. So we have, here it was Levi non-degenerate, degeneracy, and this condition, the degree of the polynomial is 2 because it's ZZ bar. And then in this paper, we are considering general polynomial of degree m in ZZ bar. And then the weight has to be changed. The weight for Z will be 1 over m. And the problem is to compute Holm. As you see, here we compute Holm M0. But here it's much more complicated. The problem is to compute Holm of P, of the model given by MW is equal to PM. And that's really a big problem. But it was done. We saw that we need, in fact, M jet. That's the wonderful things. Here you need 2 jets, and in fact, in the finite type case, you need M jet. So it's really a generalization of this. I don't know. So there is an open question session. Maybe I have time. I can already state my open question. So it's a very, it's an algebraic. There is nothing very undoable, I guess. But we don't know how to. I mean, I have my student finished his PhD, and he was not able to compute in the general case I will give you now. So it's really related to what I said now. You are in C3. You are in C3. Open question. It's the following. No, we are in C4. M is in C4, sorry. And you give yourself the real hypersurface given by M. So your variables are Z1, Z2, Z3, and W. The transverse variable is always W. And you want to consider IMW is given by P of Z, holomorphic polynomial in all these three variables, Q bar Z plus QZ P Z bar plus R of Z, R of Z bar. Sure, you want to have a homogeneous polynomial, so you arrange the fact that it's of homogeneous polynomial. This is a homogeneous polynomial. Homogeneous polynomial. Satisfying, satisfying, you have to have degree of PQ bar is equal to degree of R bar, sure. And you assume that M is holomorphically non-degenerate. You cannot talk about it's Levi degenerate. So you assume, if you are interested, I can assume that M is holomorphically non-degenerate at 0. I can tell you briefly. It means there is no holomorphic vector field tangent to M. Remember, we have real part of a holomorphic tangent. That's okay. But you don't want to have holomorphic. So, and you can understand that it's a very good generalization of Levi non-degenerate. If D is equal to 2, it's exactly the same condition. So this is a good condition. And the question is, it seems easy, but I don't know how to do it. Sure. You know, P, Q, and R are nice polynomial. They are homogeneous polynomial, very nice, behaving very nicely. And the problem is characterize in terms of P, or classify, I mean, in terms of the polynomial involved, the hypersurface M in C4 on this form, given by, this is étoile, given by star, that admit nilpotent rotation. I will tell you what it means. Nilpotent rotations. That is infinitesimal CR, infinitesimal CR automorphism, so it's element of Holm, automorphism at 0, of weight 0. You remember the rotation, it's a rigid vector field. That is infinitesimal CR automorphism of weight 0, containing whose coefficient have no W, it's only in Z. Rigid, that means no W in the coefficient. So we saw IZ DDZ for Z2. Remember, there was something. Such that it's nilpotent. What does it mean to be nilpotent? Such that there exists N bigger than 1 because of the assumption if I apply xn to my pq bar minus q p bar minus r bar, this is my, it's equal to 0. Nilpotent means that if you apply x to that, and you keep applying, and finally it's 0. So we would like to know how can you describe, in terms of P and Q and R, the M which admits such symmetries. It's very useful for some other purpose, but we don't know how to do. We know how to do only when P, Q, and R are monomial. Monomial, that's already difficult. But we would like to know for polynomial. So in C3, we know how to do it. We have a nice description, but in C4, we don't know how to do it. Is it clear, this condition? I think you just keep applying it, and when you apply to your hypersurface, it's vanishing. Why do you need n bigger than 1? Because for n equal to 1, you know that it doesn't happen, because you choose x, it's holomorphic. It's forbidden to have a holomorphic vector field applied to this guy, which is 0. But if you keep repeating, you could have nilpotent rotation, that it's rotation, this is infinitesimal CR symmetry, automorphism of weight 0 with no W. Okay, so it reminds me to thank you for your attention, and it's done, so all what I wanted to say.